Okay, so now we know the foundations of a differentially private system, which will help us to build a differentially private recommendation system. So let's get on with it. A recommendation system. What is a recommendation system? Well, a recommendation system is a subclass of information filtering system that seeks to predict the rating or preference a user would give to an item. They're primarily used in commercial applications. Netflix and Amazon could be given as two major platforms which use recommendation systems which help improve the user experience, but it's also used in Spotify for recommending songs and by Google to recommend personalized ads. There are three types of recommendation systems. Number one is context-based systems, in which basically Netflix would give you a movie recommendation based upon its description, its name, genre, the year it was released, the actors in it, etc. Collaborative based system is when Netflix or any other movie recommendation app, Prime Video, could recommend based upon how users have rated a particular film and based upon how you have rated the films you've seen, and it figures out what kind of movies you want to watch. And hybrid based system is a combination of collaborative basic recommendation systems. So it's a combination of context-based and collaborative-based system. So what is a collaborative-based system? Well, collaborative-based system has many forms, but many common systems can be reduced to two steps. It can look for the users who have the same rating pattern with the active users, and it can use the ratings from like-minded users found in the previous step to calculate a prediction for the active user. This falls under the category of user-based collaborative filtering, which is a specific application of user-based algorithm known as nearest neighbor. So let's see more about collaborative-based systems. Well, what we know about them is they're most susceptible to a privacy-based attack. This is because instead of one user, this type of recommendation system takes aggregate data from all users. On the flip side, this type of recommendation system also has huge potential gains in regards to enhancing user experience. As you can see, it is also most susceptible to a privacy-based attacks known like de-anonymization attack, which we'll learn about more in the next slide. So, privacy risks with collaborative systems. Narayan and Shmatikov, well-known researchers, demonstrated a powerful and practical de-anonymization attack linking records in Netflix price dataset with public IMDb profiles. They took their attack one step further, and they consider a scenario in which an individual maintains two different profiles. Say it's a professional blog, and there is a pseudonymous page on a social network. With occasional discussions of disjoint sets of movies, all rated on Netflix, it was impossible that they could be linked to the same Netflix price row, thus to each other. Whether movies ratings attributed to this individual are embarrassing, revealing, or at all remarkable, it is the fact that these two personas are linked that can be deceived as deeply invasive and disturbing. With a recommendation system based on user-user similarities, the attacker can also create a fictitious profile resembling an individual based on the attacker's partial knowledge and induce the recommendation system to report faithfully about all the items which have been highly rated by an individual in this case. So, how do we tackle this problem? We believe that having a differentially private system will help us tackle these problems. So let's talk about this more. What is a differentially private recommendation system? Okay, so what we're going to do in this case is we're going to offer an implementation of how a differentially private system should work. So we will be focusing on an implementation of a differentially private system. For this example, we've used the MovieLens database, which is available online. Our objective is to find whether a differentially private recommendation system would also give us as good result as a normal recommendation system without being differentially private. This is our challenge. So let's learn more. Differentially private recommendation systems are going to be tackled in 5 steps. So the 5 steps we will follow in this case are: step number one, we're going to pre-process the data, which will basically help in cleansing the data more. And then we're going to add differentially private noise. Then we're going to develop a correlation matrix. Then we're going to generate similar movies based upon the type the user likes, and then we're going to get the results. It sounds a bit complex, right? So let's see what we can do. Machine learning is hard, and that's what people use for giving recommendations, training a model, then testing it on the data set. So what we're going to do is use machine learning and use statistics and see if it can help us achieve our goals. So step number one was pre-processing the data. The first step will be this, and it will help us in data cleansing. It will help us remove the data which we will not use to contribute to our results in a vital manner. So it will remove all the irrelevant data points. So for this data set, we plan to keep only the data of those users who have rated more than 10 films, and we will also replace ratings which are like NA, in this case, the films which haven't been seen, with 0 to make things easier for us. We believe this will clean the data and deliver us more accurate results. So let's see how our data set looks like. So this is the pandas data frame in context, which has been generated using two files we got from MovieLens database, which are ratings.csv and users.csv. As you can see, after our cleansing, we have around 610 users and 2,269 columns. But you can also see there are a lot of these zeros in this. But I assure you this wouldn't affect our results. And so let's learn more about how we should make our system differentially private, which is add noise to it. So how do we do that? So as we talked about previously, we'll be adding a randomized noise to this case, which is being taken out of Laplace distribution to our ratings. Based on the current data set, we selected the epsilon, which is the privacy budget, being 2 and the sensitivity of 1. Now, let's see how our data would look after adding noise. Wow, that's a lot of difference, right? If you compare this with this, it's a big difference. You can see the values have been changed from 0 to 0.5, and it looks vastly different. So you can see randomized noise has been added to each cell, and now the data set is differentially private. So should our recommendation system work? Let's find out more. What we're going to do next is create a correlation matrix. Correlation is from the world of statistics, and it's the key to help us find out whether the relationship between the two variables is good enough or not. The variables in this case are movie ratings and movies. So it will help us in data analysis and modeling, and it's of three types. Correlation can be positive when both variables change in the same direction, neutral when no relationship exists between the two variables, and negative when the variables change in different directions. I think the graph will help you to visualize this problem more. If you feel like you want to learn a bit more about correlation, feel free to check it out. So what we're going to do next is, with the help of this, we're going to create a correlation matrix. And for this implementation, we'll be using Pearson's correlation. So as we needed covariance and standardization, we use Pearson correlation, which can be used to summarize the strength of the linear relationship between the two data samples, in this case, movies. It can be calculated as the covariance of two variables divided by the product of the standard deviation of each data sample. It is the normalization of covariance between the two variables to give an interpretable score. So let's see how our correlation matrix looks like. So as you can see, this is a correlation matrix, and it's basically a 2D matrix where movies have been mapped against movies. And as you can see, 500 Days of Summer and 500 Days of Summer, when the column value of both of these is 1, because these two movies are the same, they're gonna correlate the maximum to this, and 1 can be a maximum correlation. So this is how we're gonna use our correlation matrix to see the similarity between the two movies. Now let's see how we can get the recommendations. So how our system works is, in this case, a user will submit the movie he's watched and the ratings. We will iterate over the movies. For each movie, we will get the respective column from the correlation matrix, and then we're going to select the movies column from the correlation matrix, get the rating submitted by the user, subtracted by its average rating, which is 2.5, and then we're going to multiply it to the correlation matrix value received. Then we sort the column and return the film and their ratings. Each of these similar movies and ratings are appended in a data frame, so at the end of the things, it will look something like this. That doesn't look right, right? You cannot understand what kind of movies I like using this. So I think we can do one more thing. So the result right now, as you can see, doesn't make sense. So what we're gonna do is we're gonna sum all the values in the data frame and sort them as our so because our user likes really animation movies more, so we expect to see animation movies recommended to him. So let's see if our system can do that. Wow, so would you look at that? So in this case, the top results, as you can see, are Toy Story 3 and Ratatouille, because these two movies are what the user submitted, and these two movies he really liked. So they have a higher correlation as compared to the rest of them. So, but if you look down, it gives the recommendation of The Incredibles, Up, Finding Nemo, Cars, Kung Fu Panda, Wall-E, Monsters Inc., Brave, to name a few. So I think this system does a pretty good job of recommending movies and when the data is differentially private. But what if a recommendation system which isn't differentially private can deliver even better results, or results like this? Let's see. So when we have a side-by-side comparison of a differentially private system and a normal system, we see that the results are more or less the same, but some results are better in this case. As you can see, the third result is Sherlock Holmes in a normal system, but it's The Incredibles in our differentially private system. So we can say some results are better in a differentially private system, which is interesting to say the least. So, but I think we should do one more example to see if our system really works. In this case, we're going to see if the user likes action-adventure movies. So he's given Amazing Spider-Man 5 stars, Mission Impossible 4 stars, Toy Story 2, and Fast and Furious 4. So in this particular query, we can say that the user likes action-adventure movies more, and he doesn't like animation movies that much. So we don't expect him to get recommended animation movies. Has he got any animation movies recommended to him? Well, in a normal system, he gets recommended Over the Hedge, which is an animation movie, and the recommendation is pretty high. That doesn't seem right. But in a differentially private system, Over the Hedge doesn't exist, which is interesting. And all of these movies, we can say, are action-adventure movies, and what is pretty good and pretty cool that as he's rated Mission Impossible pretty high, which is 4 stars, you can see that on other installments of Mission Impossible have also been recommended to her, namely here and here. So we can see, based upon our final results, that using a differentially private system provided us with very good recommendation while preserving their user privacy. In some queries, we also received some better results, as I explained in the previous slide, than a normal collaborative recommendation system. So we think like if a recommendation system is differentially private, it can still deliver more or less even better results as compared to a normal differentially private system. Future scope of this particular problem exists a lot. So what you can do is you can mess around with the data set, see other values of epsilon and sensitivity, how the data set reacts to that. And we also urge you to try different methods of adding noise to the database. And our implementation was inspired from the research paper, which is Differentially Private Recommendation System by Ilya Mironov and Frank McSherry. Shout out to these references without whom we couldn't have achieved what we have. So we thank them, and we are glad that we were able to source their materials. And this is Raaghavv Devgon from the team of Megan and myself, and we thank you for watching our video, and hopefully we helped you to learn more about differentially private recommendation systems. We hope you can do something more about this, maybe work on a project on yourself more, see if this works better than our implementation. Let us know if you do, and we hope now you can go and watch some movies. Thank you very much.